Hello, ladies and gentlemen, Root Beer here, and I'll be starting another contest, another University of Waterloo contest, the 2008 Galois paper this time. So this is a written contest. You do have to write up your solutions. There's 4 questions apiece, and it's aimed at a grade 10 level, although if you are younger, you are welcome to write the Galois paper. Okay, so if you're in grades 8 or 9, feel free to try it. However, being a grade 10 contest, sometimes that means that they will reference material that you typically learn in grade 10. I think trigonometry can still happen and things like that. But if you're looking for a challenge and you're younger, absolutely. This contest is great if you're in grade 10. Of course, if you're looking for a challenge, the Hypatia for grade 11 is great as well. And all of these contests, the Friar, Galois, and Hypatia, which are written, are great practice for the scholarship paper that Waterloo puts out, the Euclid contest. Now, you can get a copy of this contest by clicking the very first link in the description, as I always do with every video. And so I'd encourage you to sort of stop right now, try the 4 questions here, give yourself, I believe it's 75 minutes, and try them out, see how far you can get, see how much you can write up, and then you can come back. I'm just going to go through them one question per video and write up my solutions. And it'll be a bit more written than when I go through a multiple choice question. But yeah, so we'll be starting with question 1 in this video. 3 positive integers a, b, and x form an O'Hara triple, ABX. We've got O'Hara triple here. If root a plus root b equals x. So it's sort of like a Pythagorean triple almost. Okay, almost. For example, 1, 4, 3 is an O'Hara triple because the square root of 1 is 1, plus the square root of 4 is 2, and that is, in fact, equal to 3. All right. So we've got 3 parts here, A, B, and C. If 36, 25, and x is an O'Hara triple, determine the value of x. Okay, this shouldn't be that hard. It's probably worth maybe 1 mark. They're just trying to get us to say, well, yes, I understand what an O'Hara triple is. I square root 36, I square root 25, add them up, and that should be my x value. Okay, so we'll just go over to our notepad here. 36 plus root 25 equals x. Just show the very quick simplification. X is going to end up being 11. Okay, so there we go. All right. So that's A done. B part. If A 9, 5 is an O'Hara triple, determine the value of A. Okay. It's going slightly in a different place. All right. So we know that root A plus root 9 must be equal to 5. So that tells me root A plus 3 is the square root of 9 is 5. And this tells me root A is 5 minus 3, or 2. So A, if I want to get rid of this square root sign, I'm going to have to square both sides. A has got to be 4. So not a whole lot to actually write up here, but you got to show your work is part of what a written solution actually is. But I haven't used any sentences or explanations. I don't think it's necessary yet. And now C. Determine the 5 O'Hara triples with x equals 6 and explain how you found these triples. Alright, well, even if they didn't command me to explain how I got these triples, this is likely going to need a little bit of explanation. Okay, so we've got 5 O'Hara triples. That means there might just be some casework involved. But we'll know when we're done if we have 5 different triples that end in 6. Okay. What could we say? Well, what can we even observe? I'm going to get a fresh sheet of paper here. So, if A, B, 6 is an O'Hara triple, then root A plus root B equals 6. I mean, it has to. That's the definition, and that's really the only thing we have to go on. Now, do they have to be... Okay, they do have to be positive integers, and that's going to help. So I might say something like square roots are always positive. Well, no, I guess square roots can be 0. I was getting at they're non-negative, but let's actually say square roots, since a and b are positive, root a and root b must be positive. Let's just say that. Okay. And so root a is going to be 6 minus root b, but then that tells me that this is less than 6. Therefore, 0 is less than root a is less than 6. I think that's pretty special. Now, the square roots here don't have to be integers themselves. They have been each time. I'm wondering if... I think root a and root b have to be integers, but I think I would have to prove that. I'm wondering... So what I wanted to do was say, okay, now root a has to be either 1, 2, 3, 4, or 5, and then from there we get a, but... And while I'm sure that'll work and give me 5 distinct triples, why is that the only possibility? Couldn't a be something like 2, and then you'd have root 2, and then 6 minus root 2? Alright, so, okay, I will answer the question. Since they tell me there's only 5, I think this is a fair jump to make. So if this is it, then... And root b is 6 minus root a, which will then be 5, 4, 3, 2, or 1. So then that tells me a can be 1, 4, I'm just squaring each of these, 16, 25, and b would then be 25, 16. These are pairs, and there's a specific order to what I'm doing. Our 5 triples, A, B, X, are, so we get 1 and 25, 4 and 16, 9 and 9, 16 and 4. Ordered triples mean that this is different than 416. And the last one, 25, 1, 6. And you can verify them. We do have 5 distinct ones. I would say that's good enough. Now, some of you out there might be saying, well, you sort of made an assumption that root a had to be an integer. For a lot of you out there, you're not going to care. You're going to say, I got my 5, I'm done. And that's fine. I've written up enough. I think I'm going to get all the marks. And no one said you have to prove that there are 5. So as long as I can find 5 distinct ones, that's enough, as long as I have some reasoning behind this. And I do have some reasoning behind this. So if you want to skip to video number 2, where we do question number 2, great, I will see you there. If you want to stay behind, I think I'm going to spend a little bit of time, just as some nice little extra practice, justifying why root a can only be 1, 2, 3, 4, or 5. Obviously, it lies between 0 and 6, but who said root a has to be an integer? A has to be an integer, yes. Who said root a has to be an integer? Well, let's explore why I think root a might have to be an integer. So why can we be sure root a is an integer? You don't have to do this, I believe, to get full marks. I'm just doing this as a little extra practice in case there were another question that did not tell me that there were 5 answers, and I would need to show, well, yes, each of the root a being an integer gives me 5 different answers, but how do I know there aren't any more? Well, let's explore it. Okay. Root a plus root b is 6. If I square both sides, that'll be 6 squared. So then that'll be a plus 2 root ab plus b is 36. The 36 here doesn't actually matter. But then root ab will be 36 minus a minus b all over 2. Okay. So that tells me, so a and b are integers. So root ab, it's not necessarily an integer, because what if a and b added up to an odd number? Then you'd have 36 minus, let's say, 7. You'd have 29 over 2. And that's not an integer. So I guess I could rearrange and say 2 root ab is an integer. Okay. That hasn't especially helped me. But well, suppose root a is not an integer. So let's do a proof by contradiction if we can. Since my first way of just sort of squaring didn't reveal anything particularly helpful. I mean, maybe this will be useful, but suppose root a is not an integer. Then root b, let's say, root b, which is 6 minus root a, it's also not an integer. Okay, now if I square both sides again, 36, this b minus 36 minus, here we go. Yeah, this will do it. That'll be 6 times 2, 12 root a plus a. But then let's rearrange b minus 36 minus a is negative 12 root a. Just for stylistic purposes, I'm going to divide by negative 1, and then we'll say 12 root a. But this side over here is an integer. And so root a, I assumed root a was not an integer. So therefore 12 root a is an integer. So root a is going to have to actually be a fraction. So he's rational. Okay. So root a might not be an integer right now, but I can guarantee you he must be rational. And so where would that go? Where would we lead off? Should I square that? Something like that. I mean, something should be wrong here. I just can't quite place what it is. Okay. So then a is going to be 36 plus a minus b all squared over 12 squared, which is 144. But a is an integer. And that tells me then 144 must divide 36 plus a minus b squared. But if that's the case, if d squared divides e squared, you can guarantee that d divides e. That tells me that 12 divides 36 plus a minus b. So not only is it rational, root a is an integer. Okay, so that was a fun little adventure. Once again, I'd like to stress, if you managed to stay around for this, you didn't need to do this. Okay? They told us in the question there are 5. We got 5. We explained how we got 5. Okay? We fiddled around with it. We said, okay, root a, root b, they have to be positive, and so that means that root a is also less than 6. Well, that gives me 5 integers, and each corresponds to a triple. We've got 5 distinct triples. We must be done. Okay? Especially for question number 1 on a Galois. But for people wondering, well, you kind of exploited the fact that they told you there's 5. There's a reason they told me there's 5, because they didn't want you doing this. But suppose they didn't. Suppose it's Hypatia question number 3 or question 7 on a Euclid where they can ask the hard stuff. I'm curious as to say, well, how do I know that root a had to be an integer? I made the assumption there. I said there happened to be 5 integers between 0 and 6. So let root a be one of them. It matched up nicely, but it wasn't exact. Okay, that is to say that, well, I went on a hunch and it turned out that it worked out and we got 5 different answers. But what if that hadn't worked out? How else would we have found root a's? How did you know it had to be integers? I didn't. I took a guess. But now I've been able to prove root a has to have been an integer. Okay, it took me a little while to get there. I was experimenting a bit. But we showed that root a has to be rational. It has to be an integer divided by 12. But then when we square it, you get an integer, so it all worked out. And root a and therefore root b as well have to be integers. So my assumption that I just say, well, let root a be 1, 2, 3, 4, 5, that worked out, and that would have been the only 5 possible values. But we've got this little extra proof here, and if you were able to follow that, great. If you were able to pause the video and deduce it on your own, even better. But now, in the future, if they don't tell me how many O'Hara triples end in 7, I'll be able to work it out. Okay? And I suspect that this will sort of generalize and actually prove that the number of O'Hara triples ending in x will always be x minus 1. Okay? And actually, I'm not going to prove that, but I'd be interested to see if somebody wanted to write that up and leave a link to that in the comments. I would love to read through that. Anyway, I think we spent a little too much time already on question number 1. Let's get ahead to question number 2. I will see you for more of the 2008 Galois next time.